Hi guys.
Hi.
Hello.
So does anybody have any questions on the anything, last lecture, homeworks, anything? All right, so today we are going to start chapter 19, which is the last chapter in the syllabus. So this chapter is about the impulse and momentum of rigid bodies. And as we have been talking about particles and impulse and momentums for particles, we were having something like, let's list them here. Let's write particles. Let's have right, so in particles, we have been dealing with the linear momentum, and it was like the mass multiplied by the velocity vector. And we also know that there's what is called angular momentum, which is the moment of the linear momentum about any point, and this will be equal to the r vector crossed by the linear momentum, something like that. And also we have linear impulse, which is the integration of the force of the force vector dt, and we have the angular impulse, which is the integration of the moment vector over the time t, and this from t1 to t2, t1 to t2, whereas t1 where we apply the force and t2 when we remove the force. So it's the time interval, the time interval of the force application on the body. Okay, so this is the equations that we have, and it was very simple because we're working with particles. But when we're dealing with rigid bodies, it will get a little bit complicated, as rigid bodies is allowed to rotate, but particles wasn't allowed to rotate because it's a very small for rotation. So let's talk today about rigid bodies. Okay, so the rigid body is something like this, and let's assume that we have a very small, tiny mass here, has a mass of mi, something like that, and this mass mi is very small, is equal to dm. And this small mass has a velocity vi as a part of this body, like has an omega, and make a general translation. And we need to get the linear momentum of this small mass mi and also the angular momentum. And when we talk about angular momentum, we need to define what is the angular momentum about. So because we are taking the moment of this, the linear momentum of this mass at a certain, about a certain axis. So we will have like to define that we have an x-axis like this and y-axis like that, and this is point P. So when we talk about angular momentum, so we will take the angular momentum of the mass mi about P. Okay, so let's first start with the linear momentum of the rigid body. So the linear momentum is very simple. L is equal to m of the velocity multiplied by the velocity of the CG of the body. Like you have the CG somewhere here. And if we know the velocity of this CG, like something like that, so this is V bar. So it will be equal the mass multiplied by the v bar, and the v bar is a vector. So the bar means it's the, as I told you last time, the bar means is the velocity as the cg, and we can write it v bar or vg. Both are the same. But don't forget that the linear momentum is a vector component. So we need to add the vector in above the v. And as I told you guys in the last announcement, be careful about the scalar quantities and the vector quantities, because I will be asking like 5 or 6 questions about what is a scalar and what is not a scalar. So like you will have to know, is the mass is a scalar or vector quantity? Is the velocity is a scalar or vector quantity? The acceleration, the momentum, the inertia, the mass moment of inertia, is it a scalar or vector quantity? You will have to understand what is scalar and what is vector. Okay, so the linear momentum is a vector quantity because the mass is a scalar quantity, but the velocity is a vector quantity. So when we multiply the mass, a scalar by a vector, it will give us a vector quantity. Okay, so if we want to get the components in x and y direction, so it will be the mvx bar, because we mean that the velocity in the x direction of the cg. So when I say bar, means it's a cg. So let's write it here. So if we have v bar x, so the bar means at the cg, and the x means in x direction. And this should be in the I hat direction. So right now, what I did, I isolated the magnitudes and put I hats to means like it's in the x direction plus m vy bar in the j hat direction. So this is how it's look like. Okay, so this is for the linear momentum. So what you will do, you will have to analyze this velocity as a Vx and Vy. So that's what I did. Okay, so let's get to the hardest part, which is the angular momentum. So for the angular momentum, it's h, and you will have to put a subscript of the point that you are taking the angular momentum about. So I want to take the angular momentum about point P, and this will be for this is small mass I. So I put I down there because this is not for the entire body. This is only for this small mass I. And what I'm doing this because it's different from the linear momentum. So here I multiply the entire mass and multiply it by v. So what I will do, I will take a very small mass, and then I will integrate to get the angular momentum of the entire body. Okay, so hb will be equal to r of point I. So let's call this point I, r point I with respect to b. So let's draw it. It will be something like this. So this is Ri with respect to B. So I stretch the line from B to I, and this will be this vector. And then I will cross this vector by the Mi, this is a small mass because I'm talking about only this mass, multiplied by the velocity of this, also of this mass, and this is a vector. So this is the velocity of this small mass, not the entire body. Okay, so let's get VI. VI. The velocity at I will be equal to the velocity of B. So if we know the velocity of at B plus VI with respect to B, as we learned it from the relative motion. Okay, so NVB should have like, so let's assume that the velocity of B is something like this. So it has a VBX and VBY. So we will have VBX in the I hat plus VBY in the J hat. And we know that the relative velocity is equal to the omega of this body crossed by Ri with respect to B. Okay, so let's draw this body one more time. Something like this. And this is X, and this is Y, and this is our mass, Mi at this point. And this is Ri with respect to B. Ri with respect to B has an X component, let's call it X, and Y component Y. So something like this and something like that. Okay, so let's get back here. So now we know the velocity. Let's substitute with VI here. And we have RIB right now. So HP for point I will be equal to Ri with respect to B has an X component in the I hat direction plus Y component in the J hat direction. And this will be crossed by Mi, and Mi is equal to Vi. So Vi, we have it here, equal VBX in the I hat direction plus VBY in the J hat direction plus omega crossed by Ri with respect to B, which is equal to X in the I hat plus Y in the J hat. So we expanded this equation and we put all the components. So if we are done with the cross multiplications here, omega by this, and then we get all this term and multiply it another cross product by X and I hat, and then this will be given, and then integrate this equation to get not only Mi, to get the entire mass, then we will be able to get, after some mass, the angular momentum about point P, it will be equal to the mass of the entire body. So let's call it M without I. So it will be something like that. Multiplied by VBY, the velocity at B in the Y direction. And this will be multiplied by the X bar. X bar is the, if we have our CG here, so X bars means the distance of point B from the CG. So it will be, this is X bar minus MVBX minus MVBX multiplied by Y bar. So the Y bar is the distance, this distance, the distance from the CG to point B, plus the mass moment of inertia about P multiplied by omega. So this, and let's put here after some mass, because it will take a lot of time to expand this equation and then do the integration, and everything actually is in the Hepler textbook. Okay. Mhm. Right. Okay. So this is the angular moment of inertia, and then let's say if point P is the center of mass, the CG of the body, what will happen? So if point P, this point, coincide with this point, the center of mass, so that means that the X bar equal Y bar equal 0, because this distances will be equal to 0. And that means that the angular moment of inertia, the angular momentum, HB, will be equal to the IP multiplied by omega, something like this. And B is actually the CG, so we can call it HG equal to I bar, which means bar means at the CG multiplied by omega. So this is how it looks like. And actually that makes sense. So let's address this body here one more time. So if we have, this is our body, and we know that the CG is here. And we have the the linear momentum like mv bar at the CG, and we know the rotation of this body, like we know I bar multiplied by omega. We can analyze this into components. So this will be m multiplied by v bar x, and this is m multiplied by v bar y. So if we want to get the angular momentum at the CG of the body, so I'm talking about the angular momentum, so it will be equal to I bar omega, because this is the angular momentum of this body, something like that, I bar omega. And the linear momentum is mv bar, which is this component. So at the CG, we have two components, angular momentum and linear momentum. So the linear momentum is mv bar, and the angular momentum is I bar omega. And v bar is represent the how much velocity, how much translation the body is making. So this is a linear momentum. And omega is representing the angular motion. So it's an angular momentum. If you want to have the angular and linear momentum at any point P, like let's assume that we need the angular momentum at point P here. So let's say that this is point P. So we need to translate all of these components, mv bar x, mv bar y, and I bar omega, take the moments of all of these about point P. So let's say for general point P, for general point P, and you want to get the angular momentum about P, so you will have to take the moment of the linear momentum about point P. So let's take the moment of this force verse. So I will have to know the perpendicular distance between this and this. So let's call this y bar because it's in the y direction. So this will be equal, and we need to determine what is our positive. So let's say our positive in this direction. So if I'm taking the moment of mv bar x about point P, it will be in the negative direction. But if I'm taking the moment of mvy bar, it will be positive moment from the right-hand rule, and this distance will be x bar because it's an x distance. So this will be equal to mvy bar multiplied by x bar minus mvx bar multiplied by y bar, this one, plus the I bar omega, because the moment is just a moment. If you have anybody, something like that, and you have a moment here, so if you're taking the moment of this moment about this point, it will be the same value of this moment about any point on this body. So this is how the equation look like. And if you keep approaching until you get to the CG, so the x bar and y bar will be equal to 0, and you will be left with I bar omega. So let's special case, x bar equal y bar equal 0 at CG. This will give you HB is equal to I bar omega. All right, does anybody have any questions on the angular and linear momentum of rigid body? Let's do some application and see how the angular and linear momentum is changing based on the motion of the rigid body. So number one, let's start with the translation. If we have a rigid body that only make translation motion, so let's assume this is our rigid body, and this is our CG of the body, and this body is only making translation in this direction. So this is the mv bar of this body. So the linear momentum L will be equal to mv bar vector, which is mv bar x and mv bar y. the j-hat direction. So how about the angular momentum? Does anybody know how can I get the angular momentum in a translation motion? How much does it will be equal? Does anybody have any answer?
Shouldn't it be 0?
Exactly. Thanks. So it will be 0 because this body is only making translation. It doesn't have any rotation. So the angular momentum will be equal to 0 here. But if you are taking the angular momentum about any other point, like if you are taking the angular momentum about point B, so you will have an angular momentum at any other point, because this will be as a part of when you take the moment of mvx and mvy, it will make moment about B. But when B is the CG, the moment of mvx and mvy will be 0. So as soon as the body is making translation, the angular momentum about the CG will be equal to 0. But if we have a point A here, and we need the angular momentum about point A, so we will need to identify the perpendicular, something like that, and the angular momentum about A will be equal to, let's put the distance first. In a scalar form, it will be the distance d multiplied by mv. So this is in a scalar form. But if you want in a vector form, it will be the r vector, like r from A to the point G. So rg with respect to A multiplied by the mv vector, which will be, if you did this, it will be the x component, like you will have to find the distance from A to x component to get y, and and also this is the y component to get x. So you will have to multiply it mv x bar by y bar plus mv y bar plus multiplied by x bar. But actually you will have to be careful about the direction. So the y bar is positive, so y bar is positive, but the x bar is positive as well. Like it's going this way. So both of them are making positive moment, and that makes sense because mv bar is making a positive moment about A, the x and y components. So it will be something like that. Okay, so let's move to the second thing, which is the fixed axis rotation. Okay, for fixed axis rotation, if we have a body like this, and this body is bent here, and this is the CG. So let's put G here, and this body is making omega in this direction. And if we want to get the velocity here, so this will be mv bar vector, and you can get v bar vector by crossing omega by rg with respect to O. So let's call this point O. You will get rg with respect to O, and this will be the v vector. So the linear momentum at the CG L will be equal to the mass multiplied by v bar vector. So it will be something like that, and we know that this will be m, and m will be multiplied by omega crossed by rg with respect to O, or you can get it separately and plug it in this equation. And the hg, the angular momentum here, it will be I bar multiplied by omega. Something like that. Yep, it will be here. But if you want to get the h at O, like if you want the angular momentum about 0.0 rather than the CG, so it will be I par omega plus the moment of these, the moment of the linear momentum. So it will be RG with respect to O crossed by this, or you analyze this into components, one in the X direction and the X and one in the Y direction, and get the component of the R, one in the X and one in the Y direction, and get the moment. And actually that is what is the cross product is doing. So the cross product is translating this into X and Y direction, like Rx in the I hat plus Ry in the J hat, multiplied cross by M, and we have Vx in the I hat plus Vy in the J hat. And when you do this cross product, it will give you the same thing. And that's what is the cross product is doing. So you either do this using the cross product, or you do this by analyzing the MV into X and Y direction, and also R in X and Y direction. So you will have to choose. And finally, if you are done with this, you will find that this will be equal to Ig omega plus the R, you can put it as R, and here it will be multiplied by M, and V is equal to omega multiplied by another R. So this is as a magnitude, so I didn't put any direction. So this will be finally Ig multiplied by omega plus M omega R squared. So if we take an omega as a common factor, you will end up with Ig plus M R squared. And this is actually the definition of the barrel axis theorem, and this will be omega multiplied by I about 0.0. So if you want to take the angular momentum about 0.0, so you either apply this, or you directly use omega I node multiplied by omega. So you get the omega, the I at the CG, and then transfer I at O by multiplying the mass multiplied by summing the mass multiplied by R square, and then you can get H about 0.0. Okay, so if I want to get the angular momentum about G, so it will be the I, the mass moment of inertia about the center of mass multiplied by omega. If I want to get the angular momentum about 0.0, so it will be the mass moment of inertia about 0.0 multiplied by omega. As soon as the O is an instantaneous center of zero velocity, this rule will be applicable. So let's move to the third motion, which is the general plane motion. 3, general plane motion. Okay, for general plane motion, let's assume that we have a wheel something like this, and this wheel is making an omega in this direction. So when it makes an omega in this direction, it will have MV bar vector, something like that. And this is an instantaneous center of zero velocity, and this is the CG. Okay, so the linear momentum will be equal to MV bar or MVG vector. So this is equal to that. Both are the same thing. And the angular momentum about point G will be equal to I bar multiplied by omega. But if you want to get the angular momentum about any point A here, or on the body here, so you will have to do the same thing. So you will have to get the I bar omega and plus this by the moment of this linear momentum about this point. So you will have to identify this is in this direction and this is D. So you will have to multiply d by the linear momentum, something like that. And a, you will have to, this one, it will be something like this. And this is the scalar form. If you want to get the vector form, it will be I, the mass moment of inertia, is a scalar, but omega is a vector, and then r vector, so r will be rg with respect to a, crossed by mv bar vector. So this is the scalar form, and this is the vector form. Okay, so what about if we take the angular momentum about the instantaneous center of zero velocity at this? So let's say if A is an instantaneous center of zero velocity. So this will be equal to h about the instantaneous center will be equal to the mass moment of inertia about the instantaneous center multiplied by omega. So what you will do, you will check your dynamics sheet and get I about the CG and then multiply the mass by the distance square from the CG to the instantaneous center. And I think in the dynamics sheet, you are given the mass moment of inertia about the center of the circular disk and also about the edge of the circular disk. So you will just like get this and multiply by omega, so you will get the the angular momentum about the instantaneous center of zero velocity. So does anybody have any questions so far? All right, so let's solve this example. So in this example, it says that at a given instant, the 5 kilogram cylinder bar has a motion shown. So the motion shown that VA is moving down with 2 meters per second. And intuitively, you will know that VB will be moving in this direction as soon as VA is moving in this direction. Okay, determine its angular momentum about point G. So it needs the angular momentum about the center of mass and about the instantaneous center of zero velocity. So you will have to identify where's the instantaneous center of zero velocity. And as you know from before, you will draw a perpendicular to the velocities, something like that and something like this, and you will be able to identify where it is. Okay, so let's draw a free body diagram to know how the velocities look like and do some geometry analysis. So this is our cylinder bar. So I know this is point A, and this is VA is equal to 2 meters per second. And I know that this is VB. I don't know. And I just identified where's the instantaneous center of zero velocity. It will be something here. So you are given VA for a reason. So let's know what is this reason. So you are given VA, so you can get the omega of this body. Because if you know VA and you know the distance to the instantaneous center of zero velocity, which will be, so you are given this as a 30 degree. So this will be equal to 4 cosine 30 and 4 sine 30. So VA is equal to the omega multiplied by R to the instantaneous center. So this is R, RA, sorry, this should be RA with respect to the instantaneous. It will be something like this. Oh, should be the other one, yeah. The R from the instantaneous center to A, because it's totally different. R A with respect to the instantaneous center. And this should be cross product. But actually, if you know the direction, I know that VA is moving down, so the omega should be is in this direction, and this is negative k hat, and this is negative j hat. So when you multiply them, it will give you the velocity is in negative j hat. Okay, so I would work with the scalar quantity and put it like omega multiplied by d, this distance d. And VA is 2. I don't know omega, but I know d is 4 cosine 30. So omega will be equal to over 4 cosine 30, and omega will be equal to 0.577 radian per second. So that's why you are given VA. So knowing omega, we will be able to solve everything in this body. So I know that this is G, the center of mass, and I can draw a line from the instantaneous center of zero velocity to the center of mass like this. And based on this, I will be able to get the velocity Vg and the direction of this velocity. So this is V. So yeah, by the way, so what type of motion is this body? Is it translation, fixed axis rotation, or general translation? Does anybody know?
Would it be general?
Exactly. Thanks. Why? Because this body is translating, so the G is moving. At some point, this will be here, so the G will be at somewhere here until it be on the ground, and G will be somewhere here. So G is moving, and in the same time, it's rotating and having an omega. So it's a general translation motion. Okay, so let's get, before we start and do anything, so let's get the mass moment of inertia about point G. This is a slender bar, and if you check your dynamics sheets for slender bars like this, and actually you will find it like this in your dynamic sheet, and we know that this bar is making a rotation about in this direction, like about this axis. And if you find the moment of inertia about this axis, it will be 1/12 ml squared. So it will be 1/12 multiplied by the mass, 5 kilograms, and L is 4. This will give you 6.67 kilogram meter square. So this is IG. Right now, I can move forward and get the angular momentum about point G. The angular momentum about point G, HG, as this is a general translation, so we will be having two components. Let's think about this for a moment. All right, so will be, let's see. Yeah, so for general plane motion, if you are taking the angular momentum about the CG, it will be I bar multiplied by omega. But if we are taking the moment about any other point, the MV will appear. And this is similar to the fixed axis rotation. About G, it will be only I bar omega. So this will be I bar, which is same as IG. So bar and G is the same thing, multiplied by omega. So I have I bar here, 6.67, and I have omega is 0.577. And when I multiply these two, it will give 3.85 kilogram meters squared per second. So this is the HG. And if you want to get this about the instantaneous center here, so you will have to take the moment of the VG, and actually not the VG, the MVG, the linear momentum. Okay, so this will be equal to, about the instantaneous center, it will be equal to I bar omega plus the moment of this, so let's call this D multiplied by MVG. So I know I bar omega, I just calculated 3.85 plus D. So let's get D. So based on the geometry, you will find that this angle will be equal to this angle, 30 degree, and this is the middle of the line. So you will find that this angle will be equal to 30 as well, and this is 2, and you will find that this is 2, just like some simple geometries. So you will find that the distance d is equal to 2 meters. So you multiply 2 by the mass 5 by the Vg. So right now we need to find the velocity at the center of mass, Vg. We didn't get it, but we can get it. Vg will be equal to the omega multiplied by this distance, d, as a scalar quantity. But if you want to get the vector quantity, it will be omega vector crossed by r g with respect to the instantaneous center. Okay, so I don't want to do cross product because I already know the direction of Vg. So the omega is 0.577. We just solve it for it. And this will be multiplied by d, 2 meters. So it will give you 1.154 meter per second. And this, when you do this multiplication, it will be 15.39 kilogram meter square per second. So this is number 1, and this is number 2, and this is the 2 things that is needed about point G and about the instantaneous center of zero velocity. So does anybody have any question on this concept? All right, so let's move forward with the principle of impulse and momentum. Actually, we talked about this before when we having mv1 plus the integration of f dt is equal to mv2. We did this for particles, but let's do it for rigid bodies. So if we have, okay, so let's draw 3 rigid bodies here. So if we have at a certain state a body that has a linear momentum, something like this, and this is mv bar 1, and has a certain omega to have an angular momentum I omega 1, something like this. And then this body has some forces and moments acting on this body for a certain time duration, like you got some forces here, and this force acted over a time t, so we integrate like this. Let's call this F1, and you have another one, F2 dt from T1 to T2. So all these impulses impacting the body, and we also have angular impulse, something like this, the integration of m dt from T1 to T2. So all these impulses acting on this body to change the linear momentum of this body and the angular momentum of this body to be something like, maybe you have a very big moment that acting in this direction and another force that acting in this direction to change the direction of the angular momentum from the positive to the negative, and it changed the direction of mv1 to be going this way, to be have mv2 vector, something like this. So let's set this into equations and see how we can do it. So as we learned it from Newtonian kinetics, that the sum of the forces is equal to mass multiplied by acceleration. And this is equivalent to m d dt of the velocity v. And when we have, so this will, down there, this will be equivalent to the sum of the forces multiplied by dt, and we will have mdv. And if we integrate these two parts, you will end up with the integration from time t1 to t2 of the sum of the forces dt and you will have mv2 minus mv1. And this give us this equation. mv1 plus the integration from T1 to Tt of the sum of the forces is equal to mv2. This is how we get this. And similarly, for the moment, we know from chapter 16, the sum of the moments about G is equal to the mass moment of inertia about G multiplied by alpha, and this is equivalent to d omega dt. So similarly, you can have sum of the moment mg dt is equal to ig d omega, and when you integrate this from t1 to t2 and from omega 1 to omega 2, this will give you ig omega 2 minus ig omega 1. And we can have similar equation, ig omega 1 plus the integration from t1 to t2 of the sum of the moments about g dt will be equal to ig omega 2, and this is our second equation. So all these have impulses and momentum. So the impulse is this term. So this term is called linear impulse because it's force. And this is called angular impulse. And impulse is the term that has time, force with time. So impulse is the force acting at a certain small time interval. So this is the impulse terms. And this is the linear momentum. This is the angular momentum. Okay, so this is a linear equation, linear, and this is angular. So this is the two equations that we have now. But I want to mention something. If you want to take the moment about any other point rather than the CG, so it will you will have the same thing, like non-centroid. So if it's, let's make it here, non-centroidal point, this equation will be, let's call this point O or B, whatever. It will be IO omega 1 plus the integration of the sum of the moments about O dt from T1 to T2, and this will be equal to IO omega 2. If this point is the instantaneous center, so it will be the mass moment of inertia about the instantaneous center multiplied by omega 1, and then plus the integration of the sum of the moments about the instantaneous center dt omega 2. So it will be, you will have the same equation. And actually, these two equations, 1 and 2, let's call this 1, and let's call this equation 2, can give us 3 equations. Let's see what this 3 equations will be look like. So let's put here the impulse momentum equations. Equations for rigid body. Okay, so as we know, any vector components, like actually this equation is vector, so we will have v vector, f vector, and v2 vector. If you have a vector equation, it can be divided into 2 equations, one in the x and one in the y direction. But for the moment equations, it's only one component because the rotation is something like this. It's only in the either the k hat or the negative k hat. By the force is something like this. It has an x component and y component. So it has a component in I and component in j. So we can have 3 components, one in the I direction, one in the j direction, and one in the k direction. So let's write these equations. So the first one, you will have the sum, okay, m v let's call it Vx1, and this is in the I hat, so let's put in the I hat direction, plus the sum of the forces in the x dt integrated from time t1 to t2 will be equal to mvx2. And the equation in the j hat direction will be mvy1 plus, I didn't put vectors because I have them out there because I know all the x's in the I hat direction and all the y in the j hat direction. So sum of fy dt mvy2. The third equation will be the one in the k hat or the negative k hat direction, which is the one related to the angular momentum. So it will be I multiplied by omega 1 plus the integration of the sum of the moments about point O. Let's put O here. This will be equal to will be I know about O multiplied by omega 2. So this is the three equations that we can use for the impulse and momentum. Okay, so let's solve a quick example on this concept. So let's assume that we have a disk, something like this, and this disk is bent here and has a radius of 0.75 meter. And there's some forces acting on this disk. Like, let's assume that we have a cable and there's a tension in this cable equal to 10 pounds. And there's a moment acting on this disk, M is equal to 4 pound-foot, something like that. Okay, the weight of the disk is equal to 20 pounds. And you are required to determine the angular velocity two seconds after starting from rest. So this disk starts from rest with this forces. After 2 seconds, you will have to determine the angular velocity. So let's see what we can do. First, we need to get the mass moment of inertia about the CG of this body. And also we need to draw a free body diagram so we can identify all the forces that acting on this body. Because in here we have forces on X and forces on Y and moments. So we need, when we have forces, we need to draw a free body diagram. So if we draw a free body diagram and we have a bin here like this, so whenever you have a bin or a support or any end condition like here, you are restraining some motion. So you will have, let's call this point A. So you will have reaction in the Y direction and reaction in the X direction. And also you will have the weight of the disk is going down and you have an external forces F is equal to 10 pounds and you have a moment M is equal to 4 pound/foot. So I put all the forces here so I don't mess any of them in my equations. And I will need I because I will have to apply one of these equations and I will do it on the CG. So if I went to the dynamics equations sheet of the mass moment of inertia of circular disk, it will be half mr square. So this will be half multiplied by 20 over 32.2 because this is weight. And r is 0.75 meter, 0.75 square, and this will give us 0.175 slug mass unit multiplied by feet square. So this is the I bar, the mass moment of inertia. And let's get the three equations and use them, these three equations. So let's, using the principle of impulse and momentum, So let's use the third equation first, this one. And to get this one will be something like I bar omega 1 plus the integration of the m about g dt from t1 to t2 equal to I bar omega 2. Okay, we know that this body started from rest, so the omega 1 will be equal to 0. And let's get the moments, and we will need to determine direction based on what I can see with this forces in this direction. So I can assume that this body is making omega in this direction. So let's assume the positive direction is this direction. So if I'm taking the moment about g, the ax, ay, and weight will have 0 moments because they are passing with the moment, with the point that I take the moment about. So the only forces that will exert moment is the F and M. So we will have, and they are constant forces. So what I can do, I can take the moment outside and multiply by T2 minus T1. So this will be equal to 4, because it's a positive direction, it's the same direction like this, plus 10 multiplied by the arm of the moment, which is the radius 0.75. And all of these will make positive moment. And don't forget to multiply T2 minus T1. T1 is equal to 0 and T2 is given 2 seconds. So it will be 2 minus 0. So this is here. And I got I bar, it's 0.175. And multiply by omega, which I don't know. So this is only one equation and one unknown. So I can get omega, and you will end up with omega 2 equal to 131.42 radian per second. So actually, this is what is required in this problem, is to determine the angular velocity after 2 seconds. So using only one equation, I was able to get the omega. So what if I use the other 2 equations? If you use the other 2 equations, like if you said that you want to get mvx plus the sum of fx dt will be equal to mvx2. So we know the initial condition is 0, so starting from rest. And you know that the CG will not moving anywhere, either in X or either in Y, because it's restrained here. So MVX will be equal to 0. So you will have that all the forces in the X direction multiplied by T2 minus T1 will be equal to 0. So what is the forces in the X direction? It's only AX. So you will get AX multiplied by 2 minus 0 will be equal to 0. This will give you that the reaction in the X direction is equal to 0. So this is equation 1, 2, 3. The 3 is the MVY, and let's put 1 plus the integration of Fy dt will be equal to MVY2. Also, the body is not moving in the y direction because it's restrained here at the center of mass. So these will be equal to 0. And you will have the Fy's multiplied by T2 minus T1, and this will be equal to 0. And Fy, and let's make the positive is in this direction, and in this equation, I made the positive in this direction. So you will have Ay in the positive minus W multiplied by T2 minus T1, which is 2 minus 0. And actually, okay, let's put it here, 2 minus 0. And if you divide by 2, this will be gone. So AY will be equal to W, and this will be equal to W is 20 pounds. So this will be 20 pounds. It is not required in the problem, but if you want to proceed or you are asked in the problem, what is the reaction at the support? So you will have to get AX and AY. And actually you can do this by doing sum of FX equal to MAX and sum of FY is equal to MAY. And it will give you the same thing. you know that this support is not moving anywhere, so the AX and AY is equal to zeros. And in the X direction, you only have AX, so this will give you AX is equal to 0. And in Y direction, you will have AY minus W equal to 0, and then you can get AY is equal to W. So either ways will give you the same solution. All right, does anybody have any question on this problem or the impulse momentum principle overall? All right, guys, see you tomorrow.
Thank you. See you tomorrow.
See you tomorrow.